Ma'am, some questions I felt were difficult, ma'am, especially from the mechanical part. Like it was doable,
Okay.
ma'am, but it was very difficult to analyze them. Like it would take more time to
Yes,
analyze.
ma'am. Actually, it has mechanics too in it, so it's a bit more like physics. Some
Yeah, but you must have read mechanics like these free body diagrams and all these things. You must have read them, right? In physics, mostly we read about all these things.
yes, ma'am. Yes, ma'am. But
Okay.
ma'am, what was happening that after doing that equations, we have to convert it to
Mhm.
transfer function. That there, I was getting confused, and that
So
took
you
my
are get
yes,
okay.
ma'am.
So you could write the differential equations properly, but then you had
Yes,
difficulty in taking the Laplace transform. Like
uh,
transfer function means you have to take the Laplace transform, right?
yes, ma'am. Because equations were too big, so while I was taking, I was getting a bit confused. I mean, in writing that, and that took a lot of time, and so I couldn't solve.
Okay. Okay. Okay, fine. Then, okay, from next quiz, let's see if we can give you a little bit more time, given that if the questions would be lengthy. Because the quiz actually, since both of us, like the faculty who is teaching section B, both of us, we sit together and we make the quiz. So we'll see that next time if we feel that the question is a bit lengthy and it will you need more time, then we'll try to give you more time. But in the next quiz, obviously, it will be the topics will be different. But in case we feel that you will need more time, we'll try to uh, give you a longer duration quiz. Okay, so let's start
Ma'am,
off.
excuse me, ma'am.
Yes,
Ma'am,
yes,
can you
yes,
upload
please.
the quiz solutions, ma'am? We will see. We will try to solve them, ma'am.
Okay, fine. Will just give me this. I'll try to upload it by this weekend. Okay.
Yes, ma'am. And ma'am, can we see our marks, ma'am, if it is possible?
Yes, I will. I will see. I have not actually gone through the because it's marked automatically, but I'll still have to go through your the answers that you have uploaded. So I'll try to finish those things off by end of this week, and then I'll let you know your marks.
Thank you, ma'am.
Yeah. So let's start with the topic where we left off. So in the last class, we were discussing about different types of control actions, right? So we were seeing that like these controllers, they can have different types of actions. So one of them was proportion. We were discussing mostly about the proportional action of a controller. Then we saw that there are other actions like integral actions. Then this derivative actions. So in proportional action, what we saw is that in case of proportional action, that is that the main drawbacks of the proportional action was that if you have a sudden change in the error signal, and if that error signal is like a steady or sustained error, then what happens is that we get a steady state error. So the output, that is the output of the whole system, which is subjected to a proportional control, that output never actually reaches the reference input. There is always an error signal, there is always a gap or an offset, you can say, between the steady state output of the system and the reference input that we are providing. So that was one of the major drawbacks of proportional control. So what can be done to decrease this or to nullify this steady state error? So in order to nullify this steady state error, what we can do is that we can introduce something which is known as an integral control. Okay. So the name integral control, it suggests that the output of, that is the actuating signal, the output of the controller will be directly proportional to the integral of the error signal. Right. Previously, when we were dealing with proportional control, we saw that the output was directly proportional to the error signal. But here, the output of the controller will be directly proportional to the integral of the error signal. So if you have if you have the error signal is, let's say, EA of t, so then the output of the controller MT will be directly proportional to integral of EA of t. So you can remove this proportionality and replace it with the proportionality constant and write the equation that this will be your output of the controller. In case of an integral control, the output of the controller will be MT equals to Ki integral EAT dt. Okay, so and Ki is defined as the integral gain. So this integral gain is integral control. This is also known as reset control. Okay, so I'll just come in a few minutes why it is called reset control. So the main advantages of this integral control is that even if you have a very small, since we are dealing with an integration means we are dealing with the area under that error signal. Okay, so if you see this figure, that for this blue or the sea green area, so here what is happening is that the magnitude of the error is very small, but it is a sustained error. But since here we are more concerned with the area, since we are taking the integral, so that means we are more concerned with the area under the curve, under the error signal. So you see that even though the magnitude of the error signal is less, however the area under the curve becomes is more. So that means that using an integral control, even a small error can be detected, and that integral control will be able to produce a control signal which is proportional to the area under the control signal. Okay, so then so some of the advantages of this integral control is that as I have already told, that it is known as the reset control. Reset control as in that if you use an integral control in your system, then the offset error that we were getting previously for a proportional control, so that means the steady state error between the output of your system and the set or the reference input, that can be nullified. So using an integral control, the property of this integral control is that they can return the controlled variable back to the reference or the set point. So even if there is a disturbance or a change in the initially there might be some change in the error signal, but using integral control, that change in the error signal can be completely nullified and there will be no steady state error. So that's why integral controls are generally known as reset control or reset controllers. But the other, so if you see this equation, so MT is equals to Ki integral of EAT. So if you write the transfer function of this integral control, so transfer function will be equals to, in this figure you see that we'll just do a Laplace transform. So in the left hand side it will be M of S, and on the right hand side you will get Ki by S into EA of S. So if you write the transfer function of this integral control, so it will be MS by EAS, which will be equals to Ki by S. So here you see that there is an S term in the denominator. So the moment there is an S term in the denominator, it means that this S will get, so 1 by S will get multiplied to the transfer function of the plant or the system that we are trying to control. So in that case, what happens is that the type or the type of the system or the order of the system, it increases by 1 because we are introducing a term 1 by S. So that so because of this integral control, so first of all you can reduce the steady state error, it increases the accuracy of the system, and but the disadvantage of this integral control is that it tends to make the system slightly unstable. Okay, so if it is responding to a very it responds very slowly to the produced error, so the response time is higher, so you need more time for this integral control to take action, but eventually once it starts generating the control signal, the steady state error that you are getting, that will be equals to 0. So now let's see why this so now let us consider that we have a control system which is given by this. So this is your output, your input is RS. So this is a unity feedback system. So let's say the plant that we are trying to control, that is the transfer function of that is given by K by 1 plus tau S. And we saw that for the integral control, MS by, if you write ES, that is equals to KI by S. Or you can substitute this, you can rewrite this as tau I by S, where tau I is the, you can write tau I is equals to 1 by Ki. So let me write it like this. So this is your integral controller. And this is the plant that we are trying to control. Okay, so if you write the overall transfer function of the system, so you can write CS by RS, that will be equals to, I'm just writing the final expression, it will be K by K plus tau I into S plus tau into tau I S square. Okay, so now you see that initially the system was the plant that we were dealing with, that was a first order system because it has the power of S in the denominator was 1. But after introducing this integral controller, the power of the order of the system, it has increased and it has become a second order system. So the moment it has become a second order system, so that means there is a chance that the stability of the system, it might be affected. Okay, so now let's say that we have a step input. We are providing a step input. So this is a step input of magnitude A. Okay, so that means RS will be equals to A by S. So now if RS equals to A by S, then you can write that, and so this is our error signal. So this error signal ES will be equals to RS minus CS. Okay, so you can write ES by RS will be nothing but 1 minus CS by RS. So now if you substitute this value of CS by RS, you will get that ES by RS is equals to nothing but 1 by 1 plus K by tau IS into 1 plus tau S. Right? So from here, if you write the expression for ES, so you will write ES will be this expression into RS. So RS is nothing but A by S. RS is A by S, and you substitute this 1 plus K tau IS into 1 plus tau S. Right? So now, so this is the final error signal that you are getting. So now what we want is that we want to see what is the steady state error that is being generated in the plant. So steady state error means we have to find out the value of ESS at ESS. So ESS is equals to, as we have seen, that this is basically time limit, time t tends to infinity, E of t, or you can also write limit S tends to 0, S into ES. Okay, so now if you take this equation and if you see that, so here it will be limit S tends to 0, S into ES will be equals to A by 1 plus K by tau IS into 1 plus tau S. So here if you see that since S is in the denominator, so you can see that the total overall denominator that, so at S, as S tends to infinity, S tends to 0, the denominator becomes infinite. So that means the value of ESS will be equals to 0. So if you have a integral control, no matter what is the type of the system that you are using or what is the transfer function of the system that you are using, you will always get that the steady state error is always equals to 0. So that means that when you have a sudden change in the error signal, and if that error signal is a continuous or a sustained over a long period of time, in that case, if you use an integral control, you will get 0 steady state error. But then, as I have already told, that the system response is slow, and it might lead to, and if you are not tuning the integral control, means if you are not selecting the value of tau I properly, then it might lead to some sort of oscillations in the system. In general, this integral controller control is not generally used as a standalone control. So I control not used as a standalone controller. In most of the cases, this is used in along with the either with proportional control or with proportional and derivative control. Okay. So here you saw that using the integral control, we could nullify the offset error which was present, which was there in case of proportional control. Now we'll see what is a derivative control. Okay. So in case of derivative control, derivative control, just give me 1 second. Okay. Yeah. So derivative control also here, as you can understand that from the name, previously in case of integral control, the output of the controller that was directly proportional to the integral of the error signal. But in case of a derivative control, the output is directly proportional to the derivative of the error signal. So that means the value of mt is directly proportional of ddt of the error signal EAT. So you can just write mt is equals to kd into ddt of EAT, and if you write the transfer function, so that means ms by, let's say, EAS, that will be nothing but s into kd. Okay, so, and kd is the derivative gain, or you can write this, or you can also write it as tau d into s, where tau d and kd are same. So similarly for derivative control also, they are also not used alone. Okay, they are always used in combination with other modes of controller, like it can be used along with proportional controller in order to make a PD control, or it can be used with proportional plus integral, and we will get a PID control, P, I and D. So the why derivative controls, they are not used as a standalone is because of the fact that using this derivative control, first of all, if you have a constant error, the derivative control will not work, even because we know that the derivative of a constant is always 0. So that means that if you have however large the amount or the magnitude of your error signal might be, if you have a constant error signal, then your derivative action will not work. Also, using this derivative control, you cannot really improve the or it doesn't eliminate the steady state error. Previously, we saw that if we are using an integral control, the steady state error can be nullified. You can make the steady state error to be 0. But in case of a derivative control, it doesn't have any such effect like that it will be equals to that the steady state error is not improved using a derivative control. Also, another problem with derivative control is that it mostly in most of the cases it amplifies the noise signals which are generated in the system, and there is a chance that it might saturate the actuator. So that's why you cannot really use a derivative control as a single control element. Okay. So, but then why do we need derivative control? What are its advantages? So derivative control is actually, it responds to the rate of change of error signal. Okay, so if you have an error signal which is changing very fast, or which is changing with time, in that case, what this derivative control does is that it responds to the rate of change of that error signal, and it produces a control signal before even the error becomes too large and your system goes to instability or something like that. So the main function of this derivative control is that it anticipates the change in the error, and it takes the corrective actions at a very early stage. Okay, so at a very early stage means derivative controls, they are very fast responding. Okay, they are very fast responding, and it tends to increase the stability of the system. It improves the transient response of the system. So if you have a system which is transient response, means what is happening in a very short initial stage. So we are not looking at a time when t is almost equals to infinity. We are more concerned in the region where t is varying from 0 to some specific point. So in the initial conditions, like initial state of the system, the response is known as the transient response. So using that derivative control, what it does is that it improves the transient response of the system. And also we'll see that in case, so if you have a first order plant, so in the, so that if you're trying to control a first order plant, like which is defined by, let's say, k by 1 plus tau s. So if you have a first order plant, then using a PD control is sometimes not very useful, because it doesn't really reduce the steady state error, unlike the integral control. But the most use of derivative control comes when we are dealing with a higher order system. Let's say you have a plant which is of second order or third order. So if you have like higher order systems, then the derivative control, the action of derivative control is much more pronounced, and there you will see that it actually improves the transient response of the system. It improves the stability of the system. So that's why you so these are the facts when derivative control is generally used. Okay, so now we'll see that how this PI, like if you combine all these three kinds of control actions, what happens? Okay, so in the first case, let's talk about PI control. So in case of a PI control, the output of the controller will be proportional to the summation of the, so it will be proportional to the error signal itself, as well as proportional to the integral of the error signal. Okay, so if you write the transfer function, if you write the output MT of the controller will be equals to Kp into Et. So this is the proportional action, and then Kp into 1 by tau y into integral of Et. So if you take the Laplace transform, so then you will get that the transfer function of this PI controller is equals to Kp multiplied by 1 by 1 plus tau y into S. Okay. So now you see that the main advantage of using a PI controller is that since we are so using this PI controller, obviously you would be able to eliminate or nullify the offset error which is generally produced when you are dealing with a proportional control. So that is one of the biggest advantages of using PI controller. So and also since now you are using like you are taking the advantages of both proportional and integral. So what happens is that it gets fast, because proportional action, that is fast responding, and integral action, it reduces the steady state error, but it is slow in response. Okay, so now if you have a proportional plus integral control, so you will take advantages of both the controllers. So that means you will take the advantage of faster response due to the proportional action, as well as you will get zero steady state error because of the integral action. Okay, so so using, and here you see that using a PI control also we are adding one pole. So there is this one S term is coming in the denominator. So that means we are adding one pole at the origin, and we are adding 1 0, which is somewhere far from the origin. So if you write, so here MS by ES is equals to Kp into 1 plus tau is by tau is. So that means here you have, in the denominator you have tau is, so that means you have a pole at 0 or a pole at origin, and then there is a term 1 plus tau is, so that in the numerator, so that means there is a 0 at S equals to minus 1 by tau. So this is somewhere in the left hand side of the S plane, but away from the origin. So since there is a pole at the origin, so you will see that the effect of this pole is basically more pronounced in this system. And this, using a PI controller, what you can do is that we can reduce the stability, but the disadvantages of this PI controller is that it gives to a higher maximum overshoot. So I'll just explain in a little bit how the overshoot is being is more. Obviously, it will have longer oscillation period compared to only proportional action, but again you will have zero steady state error. So depending on what your end goal is, whether your system can accept a little bit of a offset or not, or whether your system needs a very fast response. Depending on that, you will be choosing what kind of controller you want to use. Okay, so now so let's say that you have this proportional controller over here. Okay, so now if you write the, so just let us write the value of ES by RS. So ES by RS will be nothing but 1 minus CS by RS, and CS by RS is the overall transfer function of the whole system. So if you derive that expression, it will come as tau I into S 1 plus tau S divided by Okay, so now if here you see that if you want to find the steady state error, so steady state error is limit S tends to 0, S into ES. So that means, and this value of RS is again a step input, let's say A by S. So that means this value, there is an S in the numerator. If you substitute that, so that value will be equals to 0. So that means if you are using a PI controller in this kind of a system, the steady state error is 0. Now, if you have so now there is something which is known as characteristic equation. So this characteristic equation we'll actually talk about in more details when we discuss the time response and the transient response of a control system. So just for now, just for your understanding, so the characteristic equation is the polynomial of the denominator polynomial. Okay, so the denominator polynomial is S squared tau I plus 1 plus k kp into tau is plus k of kp. So this equals to 0. This is the characteristic equation, and the general form of a characteristic equation is given by S square plus 2 zeta omega ns plus omega n square equals to 0. So this is the general form. So here zeta is basically is known as the damping coefficient, and omega n is the natural frequency of oscillation of the system. Okay, so now if you compare these two equations, then you will find that the value of zeta is equals to 1 plus k kp by 2 into square root of tau I by k kp into tau. Okay, so this is the value of the damping coefficient when you are using a proportional plus integral control. Now, if you have only let's say instead of using PI, you had only I control. So if you have only I control, in a similar way, you can write the characteristic equation and you can find that the value of zeta in that case will be equals to 1 by 2 square root of tau I by k into tau. Okay, so you can see here that So if you are using only the I control, so you have this expression, and when you are using both P and I, so the term Kp or the proportional gain that comes in the denominator. So if you can control or you can change the value of Kp, so that gives you an additional degree of freedom on the control of zeta. So here you can change, in case of only integral control, the value of zeta can only be changed by changing the value of tau I. But here when you are using P plus I, then zeta is dependent both on tau I, so you can change tau I to control zeta, and also you can manipulate or change the value of Kp so that the value of zeta is changed. And since Kp is in the denominator, you see that if the value of Kp increases, so if Kp increases, then the damping constant zeta also increases. So the damping constant zeta increases means the amount of oscillation which is happening in the transient state, that will be less. Okay, so obviously if your value of zeta is equals to 0, so that means there is no damping. So if the system is oscillating, so that oscillations will keep on continuing throughout the time. But the moment you have some kind of damping, so that means if you have more damping, so the oscillations will die down at a faster rate. And if you have less amount of damping, so that means the oscillations will be there, but it will take more time for the oscillations to die down. So that's why you see that if you have a proportional plus integral control, so that actually improves the transient response of the system, and the system will have less oscillations. So in case of PI control, you have the transient response improves, and the system will have less oscillations. So this is how we are actually and also since this error signal, the steady state error is 0, so that means the steady state response is also is quite good. So that means you have using PI control, what you can do is that we will be able to improve both the transient response as well as we can control the oscillations, and the steady state error is also minimized. Okay, so this is sort of these are like the advantages why we are or the properties of using a proportional plus integral control. So is this clear till now?
Yes, ma'am.
Okay. So now let's talk about proportional plus derivative control. So in case of a proportional plus derivative control, so you will have the action of both the proportional action as well as the derivative action. Okay, so if you see this diagram and if you write the transfer function of the PD controller, so that will be given by Kp into 1 plus tau d into S. So if you see that the transfer function here, you see that we are introducing only 1 0 when we are dealing with a PD control. We are introducing 1 0 to the system. Okay. So introducing a 0 to the system, that actually if you have a 0 in the system, if you introduce a 0 in the system, that actually improves the stability of the open loop transfer function. But if you add a pole to the open loop pole to a system, then it actually reduces the stability of the system. So here in the previous case when we were using a PI controller, in case of PI controller, we were introducing one pole at the origin, as well as we were introducing 1 0 at some position in the left hand side of the S plane. But in case of PD control, we are not introducing any poles into the system. We are just adding 1 0 at a location depending on what is the value of this tau d. Okay, so if you can choose the value of tau d in such a way and you can place this 0 at a proper location, that actually improves the system stability by a lot. So using PD controller, it improves the transient response. Transient response, again, it improves because using derivative control, since it is sort of giving you more like it is acting on the rate of change of error. So that means, and it is very fast acting. So your response, the transient response improves when you are using a PD control. And in case of PI control, mostly the main advantage of, even though using PI control also you are getting slightly improved transient response, but the main advantage of PI controller comes in the improvement of the steady state performance of the control system. And okay. Now let's say that so if you have a system which is a first order system like k by 1 plus tau s, in that case the action of this PD control is not much pronounced. Okay, so now let's say that you are using a PD control, and the system or the plant that you are trying to control, that is a higher order or a second order plant. Okay, so this is your PD controller, and this is the plant that you are trying to. So let's say that plant transfer function is, this is a second order plant which you are trying to control. Okay, so now we'll see that the stability of higher order processes, they are actually improved. So stability of higher order plants or processes is improved if you use a PD control. Okay, so let's say that for this system, if you had only P control, so in that case, this Cs by Rs will be equals to Kp by J square plus Kp. Let's say if you have only P control. So that means if you write the characteristic equation, so the characteristic equation is Ja square plus Kp is equals to 0. So here you see that if you compare it with the standard equation, so 2 zeta omega n s plus omega n square equals to 0. If you equate these two equations, you see the value of zeta is equals to 0. So that means there is no damping. So if you are using only proportional control and you are trying to control a second order plant, so there is no damping, means that the response will be an oscillatory. So the output will have oscillations, and these oscillations will not die down because there is no damping. Now if you use PD control, so in case of PD control, then you will again write the transfer function. So the transfer function comes like this, Kp into 1 plus tau ds into J square plus Kp into 1 plus tau d into s. So here now in the second case, when we are using a proportional plus derivative control, the characteristic equation becomes equals to 0, and from here you see that the value of zeta is equals to tau d by 2 into square root of Kp. Okay, so that means that if you increase the value of Kp, the value of zeta also increases. The value of zeta increases means the oscillations that are there in the system, so that oscillations will decrease, right? So that means that the stability of the system that is improved, or this PD controller that is able to improve the stability of the system by reducing the number of oscillations when we are dealing with a higher order plant. So mostly this PD control, they are generally used for higher order. They are not used in when we are dealing with a first order plant. Mostly for second order plants, we are using this PD control. Now, if you so these were like PI, PID separately. Then we have talked about PD and we have talked about PI. So the third type of controller, which is the most popular type of controller, that is known as proportional plus integral plus derivative, or in short, this is known as a PID controller. So this PID controller, basically it is used, it is, as I told, that this is the most commonly used controller in all kinds of industrial control applications. So they are used for different kinds of processes, like if you want to regulate the temperature, if you want to monitor the flow, pressure, speed, and all different kinds of process variables, whatever, in most of the cases, this PID controller is basically used. So why this PID controller is used is because that you will have the advantages, you can exploit the advantages of both proportional, integral as well as derivative controls together, and you can change the you can tune the parameters, like you can change the value of Kp, tau d, tau I. You can have a control, or you can change these parameters in order to meet what is your end outcome. So depending on what your system needs, accordingly you can change the parameters Kp, tau d and tau I, and you will get a satisfactory response. Okay, so basically if you write the transfer function of this PID control, so transfer function of PID control will be given by Kp into 1 plus tau d into S plus 1 by tau I into S. So first of all, the order of the of this controller is low. So if you can select the value of Kp, tau d and tau I, then you can manipulate, or you can make the system perform in a way that you want. Okay, so one pole is obviously fixed because there is tau is in the denominator. So one pole at origin will always be there, but there in the numerator you will see that you will one pole is fixed, and in the numerator you have 1 plus tau is plus tau I tau d into S square. So this is there in the numerator. So if you equate this to 0, so you will have two solutions to this equation. So that means there will be two zeros in the system. So by using a proportional PID controller, we are introducing one pole at origin, and we are introducing two zeros in the system, and the position of these two zeros can be controlled by the value, by changing the value of tau I, tau d and Kp. So depending on where you are placing your zeros, accordingly you can improve the stability of the system as well as the desired performance. Okay, so the main advantages of using this proportional and PID controller is that, first of all, you will not get any kind of offset. Steady state error will be equals to 0, and also it will reduce the maximum deviation or the overshoot in case there is some oscillations in the system. So the maximum value of the oscillation, that will be reduced. Also the time for which the oscillation is happening, so there will be an increase in the damping coefficient. So that means the oscillations will slowly, or depending on the value of zeta, that will slowly decay down and eventually give rise to the desired response. Okay, so using this PID control, we are actually exploiting the advantages of all the three controllers taken separately, and you are combining everything, and you are tuning the values of Kp, tau d and tau I, and in order to get a desired response. Okay, so when we are actually, when we will talk about, this is not needed. Okay, so in later on, we will talk about the transient response or the time response of a control system. So if you have a first order control system and and if you have a specific input, then how the output of the system changes. So we'll discuss about those things later on. In that, while doing that discussion, these things like this concept of overshoot or damping coefficient or the oscillation in the output, these things will become much more clearer. Then you will be able to relate whatever I'm telling right now with the actual system. Okay, so but overall, you are getting the point of why, what are the different advantages of this proportional, integral, derivative, or PID, PID, all these kind of controllers, right?
Yes, ma'am.
Okay. Okay. So next, the next topic that we will be discussing is the topic of block diagram. So we have already in the first module we have already talked about what a block diagram is. So basically, so just to recap, so a block diagram is basically a pictorial representation of the functions which are being performed by each component of a control system. So a control system, as you know, that it has a controller, it has an error detector, it has a plant. So a block diagram is basically you are representing the interrelationships of the various components of the system, and you are connecting each block with the system variables. Okay. So basically, in each block, what we each functional block, basically it is the mathematical operation or the transfer. Basically, this mathematical operation is nothing but the transfer function which is generally entered in the functional blocks. So this mathematical operation which is performed on the input in order to produce a specific output, that is known as a functional block. And obviously a block will have an input, it will have an output. So the direction of the arrow, it determines or it indicates the direction of flow of the signal through the block. Okay, and also another important thing is that this block diagram is not a unique representation. Okay, so you can, if you have a specific system, you can represent the system by different combinations of a block diagram. So the overall transfer function of the system will remain same, but you can have multiple combinations of block diagram in order to reach that final transfer function. Okay, so now we'll talk about a little bit about the basic components of a block diagram. So in case of a block diagram, so this is a block. So this is GS is a functional block, and GS is the transfer function of the block. Transfer function of the block means and this is the input to the block and this is the output to the block. And what is the function of this block? So whatever is the transfer function of the block, that gets multiplied to the input to this block and it generates an output. So that means the output CS will be equals to the input RS multiplied by the functional block, the transfer function of the block. So CS will be equals to RS into GS. So now there are two different types of components. So one component is the summing point. Okay. So summing point, or you can say that we have talked about error detectors, right? So summing point becomes, it is generally indicated by a circle with a cross in between. Okay. And it can have like multiple, not necessarily that it has only 4 inputs or outputs. It can have multiple inputs also. And whatever and how this summing block, whether the signals which are going into the summing block, whether those signals will be added or subtracted, it depends on the sign. Okay, so if you have this kind of a sign, so here in this error detector, you see there are 3 signals which are being input. There are 3 input signals, and the output signal of the error detector will be equals to, so RS is going in the sign is positive, so RS is plus, XS is also going into the positive end, so that means you will have RS plus XS. However, YS, you see that it is going into with a negative sign, so that means the output will be RS plus XS minus of YS. Okay, so the other thing which is which you need to so the inputs to the summing point should have the same dimensions or units. Otherwise, obviously, if you have like let's say if you have temperature as one signal and you have pressure as another signal, so obviously you won't be able to add those things up, even though you can just write the terms, but you won't be able to add those two signals. So the inputs of the summing point, they always should have same dimension and units. Then only you will be able to add those signals together. Okay, so and then the second component of block diagram is known as a branch or a takeoff point. Okay, so a takeoff point, basically it means that the point from which a signal from one block goes to other blocks, or it goes to another summing point. So let's say you have, so there is this path. Okay, so this point will be known as a summing point. So this is basically this is a takeoff point, not summing point. This will be known as a takeoff point because from here we are taking out one signal. So this signal will either go to, let's say, some other block, or it can even act as an input to a summing point also. So wherever there is a branching happening, so that is known as a takeoff point. So this we have already. Yes.
Continue next class, ma'am. We have a class now.
Oh, okay, sure, no problem. So, so the concepts of like this PID, all these controllers, those are clear to you, or do you have any doubts?
No, ma'am. Once we'll go through the slide and ask you,
ma'am. Okay, sure. Okay, thank you then, and we'll meet tomorrow again.
Thank you, ma'am.
Thanks.